get quite the place. So we'll continue from yesterday as we were discussing different modes of 3D printing. What I find importance is also how to know how a 3D printer works. Just to query, has the recording started? Okay, great, thank you. Right, so we were discussing, you already know, have come across about FDM based 3D printers. Now we have slowly moved into SLA and then SLS. There are furthermore which I'll discuss. I just want to know, in what format are you comfortable with? Would you like me to draw the diagrams by hand so that you identify each components individually, or do you want to see pictures? I can do both. So just pictures or drawing. Can you type it on the chat box? Drawing. Okay. All right. Personally, I feel drawings are much more convenient because there is a sequential approach of each component, one above the another. Hence, I feel that way we can understand quite a bit. So it's a 2-hour long lecture. Usually I don't do that long lectures, but nevertheless, we are going to, let's see, cover quite a bit of topics. Not only some types of 3D printing, but then again, some backdrops, which I believe one should always know from an engineering discipline, so as to develop a firm grasp over how does a machine work. Okay, so last time regarding the FDM, I was speaking about how these motors control X, Y, and Z stages. So this time, let's step back a little and really know how a computer controls X, Y, and Z stages. Okay, I believe that will be of some importance as to why you would know how you can extrapolate such systems into civil engineering domain, of course. Just another query. Anybody other than civil engineering over here? Anyone who's not from civil engineering discipline? Can you please type it on?
Sir, I am from mechanical department.
Okay, great. Great. Anybody else? You can type it out on the chat box so that way it remains sort of concrete. Triple E. Okay, that is awesome. Right. Any other? Okay, great. People from electrical electronics. Brilliant. Perhaps they would find some elements relevant, but just because you belong to civil engineering and you should not know how a 3D printer works is, I believe, not a fair excuse. So let me get started. I'll switch on the slide. Do let me know if you can see the screen. You have to give me a voice cue, only then I would know that it is visible.
Yes.
Yes, okay. So if you remember the X, Y, and Z stages of 3D printer here, which related to FDM, is the most common architecture which you might find relevance when talking about a civil-based 3D printing project. All right. However, there are plenty of domain in relation to it where you can explore. I just come across some of them. Okay. Let's start with control of an FDM based 3D printer. All right. So one of the important concept here, one should understand that all the 3D printers are now microprocessor controlled, which means that the fundamental bridge between commands and execution is held by a microprocessor. In short, I'll write it as MUC. It's nothing but a microprocessor. I'm sure you must have heard about several microprocessors, including the one that is operating while you are using this video call. Okay. So over here, what we understand is that the microprocessor will fetch some command from memory. Okay. And then eventually give certain output that controls motors, extruders, which are again motors, heating element, if you remember, and then finally, what else? Maybe cooling fans, okay, all the heating elements. So several output are produced. Then again, one important characteristic here is that you can also put some sensors. So if you remember, there were a couple of switches I was talking about, just so that the 3D printer knows that it has reached its maximum workspace. Okay, if you remember this particular switch. Okay, relay switch. All right. So these sort of elements will act as an input to the microprocessor. All right, input in terms of sensing element. So a 3D printer would definitely have hence some input elements, some output elements, and some memory access where it will lead to some programming. So what a microprocessor does is it converts this information and creates some binary voltage signals. Okay. Most conveniently, what is used is called something called as PWM, which is a pulse width modulated signal. So let's start with a concept that if I want to turn on and off a simple LED light bulb, okay, then I want voltage in and voltage out. That's very easy to understand. So whenever I close the circuit, there's a 5-volt supply, and whenever I open the circuit, there's a 0-volt supply. So what we are doing is that we are switching between 5-volt and 0-volt so that we get a constant pulsation in due time. Okay, so instead of supplying a continuous 5-volt, what we are doing is giving a pulse like this. So what is the average voltage? Of course, it will be somewhere over here all along the time t. Okay, the same thing if I replace this LED light with a motor. Okay, what happens is that because we are operating at some frequency, eventually we are sending a V average to the motor for which it is turning. This way, and switching off, I can control the displacement of the motor. As you know, if you supply some voltage, it will extract some current, and then eventually it will generate some displacement in the shaft. Okay, so this sort of logic can be easily developed by simply a binary system of ones and zeros in a microprocessor. Okay, and I'm not going in depth what's the architecture of a microprocessor, that it's not the scope. But what we should understand is that beneath every 3D printing operation, there is a microprocessor dedicated to this system. All right. So now, as there will be a scan through the memory, okay, there will be a scan through the memory. It will try to read the instructions that are put in place. In our case, we give a 3D model, and the entire set of instructions is being interiorly developed. We do not interfere in the development of the internal instructions. we'll see very superficially how these instructions are generated, and then eventually uh, these memory scan commands are then loaded on the microprocessor as commands. So for each command, all the PWM signals are generated as per the requested sequence. Okay, all of them. Okay, because it is convenient, one and zeros. All right. In some cases, when you are working with large 3D printers, or maybe in some construction based 3D printers, you would often realize these motors tend to reach around 5 to 15 horsepower of power. In that case, you can simply not put a microprocessor on place, because the power delivered by the microprocessor will not be sufficient, and hence we need an intermediate component called a motor driver. People interested in robotics would already have come across this part. Okay, motor driver, and which is then fed to a motor. All right. uh, if you are finding it uncomfortable for the fact that this might not be very relevant, but you will surely see how relevancy occurs, okay, through this. Right now, what happens is, for some PWM signal over here, write it down, PWM signal over here, the PWM signal flows into a motor driver, which then converts or rather amplifies, which means that PWM signal into some gain, say 505 amperes, will lead to what? Or let me put it as 220 volt. Okay. Into this will of course give you a voltage profile that will fluctuate between 220 volt and not necessarily zero, but towards zero. Okay. If you multiply this, you get equal to this sort of a voltage profile, which is the work of a motor driver. So fundamentally, beneath a 3D printer, there's a motor driver which is connected to the motor, and it is being controlled by a microprocessor. All right. So whenever there is an interrupt by the input surfaces, say that relay switch that I recently marked by red, that has been kicked off, it will override these commands and cut off the PWM signal so that there is no motion of the motor in the X stage. All right. So this is one elemental form of operation, how a microprocessor controls 3D printers in particular, or any system, for any system that has motion in general. Okay, this is how a microprocessor controls. Now, what is the command or the memory allocation based upon? What sort of instruction does the microprocessor have? Definitely, the instructions have to be in some sort of a binary command. But the next level of information that we can decipher by simply talking about motions is something called as the, sorry, G code and M code. I just want to know if you have ever heard of this term before. G code and M code. I would like some feedback. Have you heard about G code and M code before? Great. Okay. Okay, that's one. Okay. Is it already covered? Then I'm not going to touch that.
You heard about the G code.
Is it covered? Do you know what does what? Okay. 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 All right. All right. No problem. Let me start afresh. So what's a G code and M code? This is basically a series of syntax that is used to deliver instructions to any controller which tries to make motion through a motor. Okay. So what sort of series instruction? G code implies that all movement are labeled under this series. What sort of movement are we talking about? It can be linear motion. It can be rotary motion. Okay, it can be also stage-wise motion. All right, but with M code, these are for auxiliary systems. What's the auxiliary system that we are talking about? Auxiliary system are turn, extruder, on/off, turn, heater, on/off. Okay, so these are the entire different system. So here further instructions can be end program, go to home, change filament, etc. Okay, so M codes are for auxiliary systems, which might differ from 3D printer to 3D printer based upon capacity. Okay, but this G code is essentially trying to make movement for the X, Y, and Z stages. So it is very convenient for us to understand that in a Cartesian plane, we can easily move from one point to the other point by simply drawing a line. But just try to think about how a motor will execute this process. Is it going to move a little bit of X and then Y, some X and then Y, some X then Y? Okay, is it going to be such like that? Or we are going to have a refined version of this, a continuous motion? Okay, these are the things that turn the 3D printer into a really capable machine when it comes to accurately or rather intelligently writing the code of motion. Okay, so there's a huge chart of several different codes. Most popularly, was used with CNC machines. As you have seen in workshops, you have got lathe machine, drilling machine, milling machine, shipper machine. However, if you automate those machines, they turn into numerical control machine, and these had primarily actually used CNC code. But now the same code, because of its efficiency, is being implemented in 3D printers. Okay, so if you simply write, I'm not sure if I'll accurately describe it, G90. If I write a line like this, the extruder will move from say 0, 0 position to X20, Y20. Okay, this is what's going to happen. All right. Then comes the concept of interpolation. There's something called as absolute interpolation and incremental interpolation. What's that? Absolute and incremental. Okay. What's with absolute interpolation? So this absolute interpolation will assume that all the reference points of a 3D of a 2D layer, okay, 2D system that you are mentioning will be based upon the original Cartesian coordinate system, which means that I will start off with, say, for example, 2, 2. So the next point, if I have a displacement of 2 over here, it will be 4, 2. Okay, and likewise, if I have a displacement of 2 over here, it will be 2. 4, 4, and here it will be 4, 2, 4. Okay, if I have to express this system in absolute coordinate system, I'll start off by adding from the 0th point. But in incremental system, I'll start off by adding relatively, which means that here, if the command is, say, G90, move from origin to this particular point, but the command will be G90, X2, Y2. Okay, then I would want it to move to 2 more units, but this time I'm going to mention G90, X4, Y2. Okay, then move to that position. Okay, G90, X4, 4y4, right? And then G90 x2 y4. All right. But in incremental format, what we will consider is wherever the extruder has been last set at, that goes to 0 position. Okay. So here, say it was at 0, 0 initially. I took it to 2, 2. This point will turn out to be 2, 0. Then this point will turn out to be 0, 2. This point will turn out to be minus 2, 0. Okay. So G90, this will start off with x2, y2. How many units? Only x I need to proceed. Oh, sorry, it will not be G90, G91 now. So G91, x2, y0, G91, x0, y2, G91, x minus 2, y0. Is this concept clear? Please give it a thought.
Yes.
Yeah. Others? How absolute and incremental concepts happen? Right. Okay. Fine. So why do we need to talk about these systems is because, say, I have a particular surface, a particular plane of which the coordinates have been registered by the slicer, the slicer in Ultimaker Cura. I was unable to recall the name yesterday, but I got it. Say the slicer that you have been using is creating these 2D slices, okay? And then if you open the STL file or if you open one slice at a time, you will realize that there will be something called as a closed loop. And then you will find all the coordinates of this particular point. Essentially, what another algorithm is doing, converting all these coordinates that is available into understandable G code and M code for the machine to understand. Then again, the G code and M code is further converted into assembly level languages by the microprocessor encoder. Okay, so this is the flow of operation, how the coordinates from a solid model is converted into G code and M code and eventually to the assembly level language by the encoder, and eventually some voltage signals are generated for the motor to operate. I just want to know if this flow process is clear for everyone. Do you want me to repeat it? Or any part of that you want me to repeat?
Sir, what is G like coordinate? Like G1, G91,
Think about
G90.
G as geometric. Sorry? Yeah. Can you repeat? Can you repeat the question? Sorry, I interrupted you in between. Yeah.
Sir, what is the significance of that G90, G91 coordinate?
Okay. See, say we know X and Y, right? We know this part, but I want the machine or the controller to understand that it should move in a straight line. Okay, so for that I want to use G90. If I want it to move straight line but with incremental coordinate system, I'll use G91. Okay, so if I want to use incremental system but use some curvature, G certain 70, 80 things will come into place. Okay, if you have to repeat a process, say I want this revolution to happen multiple over and over again, then in this case what I will do is just ensure one G code that repeats one process. So that's perhaps G40 called something called as scan cycle. We are not going to much detail, but right away, because you are curious, let me show you one software which is available free of cost and it is online. You don't need to install or download anything. I'll just switch my screen. The software is called NC Viewer. Okay, it's a G code and M code simulator. Tells you through which part exactly right. The extruder will process. Yeah. Can you see this? This is ncviewer.com, free of cost. Okay. It is available open source. So there's a coordinate system that we are looking at. There's a small button called sample. So what I'll do is just load this sample program. Okay. And as you can see, if you want to say 3D print this part, or if think about it in this way, even if you replace the extruder with a drill machine, and if you put a solid block of metal or wood or paper, it is going to cut out all these parts. Okay. Can you see? That's a model NC viewer. So all these tool trajectories are given, and on the left of the screen you can see all the G code and M code. All right. Okay. So if you remember G90, absolute system, not incremental, and all these coordinates are mentioned. Okay. And as I'm moving through the cursor point sequentially, you will see that the tool keeps on moving. Can you see that? The tool is moving. All right. So this is a simulator on how your extruder will move. Why do I think this is important for you to understand is because say you are working on a really large scale platform, okay, and the terrain is not a flat one, or you're using cement to build houses. So it's always convenient to actually simulate what sort of extrusion or what sort of path trajectory that you have generated. Okay, and that way you can simulate all the parts. So what you can do is take it back to the origin, and it's going to do this 3D printing process, and it's actually showing how the G code M code moves. Doesn't matter if it is a 3D printing process or a CNC printer. And you can write your own code over here, by the way. All right. Yeah. So let me give it a try. So if I start with a new file, I should copy some part of it because some stuff are predefined. So let me copy this element into the new code. Okay. So N10, N15, N20, these are nothing but line numbers. Okay. The reason that we use N10, N15 and not 1, 2, 3, 4 is because say somewhere you want to edit. Okay. Then here, say I want to add a line, I can simply go ahead and write N11, G90. So it's always good to have some bracketing, some margins by which it should operate. Okay. So here, let me plot. Right. So can you see the tool trajectory? It got really large. Yeah, plot. Okay. Right. So can you see a small trajectory has been formed? Okay. If I, yeah. So that's the motion. It's going from this particular location. I believe we had mentioned some coordinates over here. G0. Let me shoot it at X0 and Y0. Now, yes. Yeah. Now we are looking at a vertical displacement represented by Z 1.4. Okay. Can you see this particular line? Z 1.4, and it's going to move this element. Say at this moment of time, you want to start the extrusion process. You will write an M code for it. Okay. That start the extruder. So that's how the commands differ from a G or an M. Okay. Is that part clear?
Yes, sir.
Okay, any questions till now? Anything at random? Do you think this part was useful in understanding how a 3D printer would operate? And should I repeat any part?
Yes, sir.
Thank you. Anything? Any feedback? Because we are going to move in some different sections from time to time. Okay. Right. Okay. So that was G code, M code. There are different codes further, but I believe once you have a look at it with a simple code, then it shouldn't be a problem. Okay, with NC Viewer, you can try this particular example. All right, and do let me know how does G91 works or G90 works. Okay, you can trial and error. It's pretty simple. That's very basic. Okay, right now. This sort of a process of converting in G code and M code is pretty fundamental, except in case of SLA and SLS, where we not only need to control certain stages, but we are now working with galvanometers, which cause some linear displacements. And further, what we end up doing is we establish some protocols. Okay, so what are the protocols? Now let me define this for you. These protocols are for SLA, SLS based systems, which do not have X, Y, and Z stages, which use mirrors or flexure mechanisms so as to achieve a particular amount of displacement. These protocols are roughly Xy2 100 and the other was SL2 100. Okay, I really do not have any idea about SL2, but let me talk about the Xy2 coordinate system. So what happens in Xy2 protocol? In Xy2 protocol, the microprocessor allocates 20 bits. Okay, what is bit? Bit is nothing but one information. All right, if you remember ones and zeros. Okay, so the top three are the first three rather are control bits. Control bits. Okay, next 16 bits are X, Y, and Z information bits. Okay, and eventually we have a parity or something that is used for verifying if the sequence of command is correct or not. That is called a parity bit, and eventually a parity bit. So 3 control bits plus 16 position bits plus 1 parity bit. That's an XY2 system. Okay, these informations are channeled through different pins across the microprocessor, whereas in SL2 it's a serial communication, which means that right away from one pin all these bits will be covered up. So I mean, there's no technical relevance. I mean, there is relevance, but it should not make you bothered. What is this? What is that? It's just that this is something to know. Why? Because say one day you work with a 3D printer which is novel, which is new, yet to be released, yet to be commercialized. In order to be accepted in all the 3D printing industries or industries which use 3D printer, this sort of communication protocols should be known. At least you can standardize your machine when you make it. Okay. All right. So this was all about control of a 3D printer. What I can imagine from here, what's the takeaway is that you know how XYZ motion of a 3D printer works. One thing. Second, you know what is underneath a a 3D printer, which is a microprocessor, and some programs that encode and decode information, some inputs, some outputs, and eventually certain protocols and languages, which are G code, M code, and the protocols being XYZ and SL2, Xy2 and SL2 protocols. Okay, so this kind of summarizes what we require. So that leads us to the next concept of tool path planning. it's still a tool path planning, even though we really do not use a tool over here. Have you come across this concept called tool path planning? Is it already taught in the course? Is tool planning already taught in the course?
No, sir.
Okay. All right. So what happens is, even with FDM or with SLS, SLA machines, you usually end up having a geometry which has to be filled, isn't it? This has to be filled. This space has to be filled. So one, out of curiosity, would always ask to reduce the operation time, which way will be the shortest one. Okay, so there are different toolpath planning algorithms, and these toolpath planning algorithms actually start from the STL file, which you know that some triangulations happen. Okay, triangulations of closed loop, which means that all the triangles that are made eventually form a closed loop, and within that the operation of filling has to be carried out. And it is definitely, there is no one way of doing it. What you can do, if you have seen of FDM, or you will shortly see what an FDM process does, is it will try to either further dissect the part in based upon the requirements. Say you have a hole in center, okay, or else it will try to find out the best possible way so that the optimum surface structure smoothness is achieved, as well as the time required is absolutely lesser than other processes. So there is some XYZ scanning that you can do for a 3D printer process. Okay, and then for the same material, you can use a vertical scanning approach. So there are zigzags and plenty of scanning patterns that are available, not going into depth of them. But this toolpath planning is redundant in cases where you are working only with the edges and nothing else in between. Okay, now this is of prime relevance because in civil based 3D printing projects, what you are creating is space. You do not wish to create a solid structure until and unless you're of course creating supports for that matter. So even then, this path trajectory do not really matter, because what you hear is maybe do some zigzag operation and then fill the constituents of the part. Now there is an option called fill density. Okay, this fill density, if you put it up to 100%, it should essentially make a 100% concrete solid part. Now can you tell me if that is possible? Can you make a 3D printed part which is entirely solid and has no holes? Is that possible? A quick pop-up question. No. Why so? Why is that so? Or can you think of a criteria under which it can perfectly make a solid part? All right, this will be a Google element. I'm repeating the question. Do look at it up, because these are a sort of concept-based situations. Has nothing to do with engineering in general or a discipline of engineering in general. Okay, try to figure out how to achieve 100% density in a 3D printed machine. Okay, try to read some article or even query yourself within introspect. Okay, how do you achieve 100% density in a 3D printed part? Now, of course, as you will see that this is a limitation that we can rarely produce 100% density 3D printing part. Of course, it becomes a subject of interest or a challenge that engineers take upon to move into certain other modes of 3D printing where you actually can make 100% 3D printed parts. Well, this is not the answer for the previous question though. I mean, in FDM, how do you ensure 100% density of a 3D printed part? Okay, so in 3D printing, we have come across this hindrance where 100% field density is impossible, and hence we would like to explore some process where we would like to incorporate certain elements or reform in how 3D printing is carried out so that we can achieve 100% field density. Say, for example, what if one single layer is printed at one single exposure, which means that it's like I'm taking a piece of paper with a small cutout of that body and immediately pasting on top of it. That way, we are going to get 100% field density. So, like I mentioned, if I cut out a paper of one layer and then paste it over another body, I'm going to get 100% density. This process is called Laminated Object Manufacturing 3D Printing, or LOM. Okay, this was previously also done to make engine assemblies, but now it has gained popularity because the advent of additive manufacturing. And the other process is called digital light processing, DLP printing, which again throws a single exposure of light and then builds up a one single 3D printed part. Now, these are the topics that we will cover shortly in this particular lecture. And I just want you to have some relation that what is the problem and how these solutions were overcome with this other inventions of 3D printing. Okay, let me continue with this. Say we'll take an object in general, plastic grill. Okay, this part has to be 3D printed. Okay, so I want to know that what is the optimum orientation. Okay, that's one of my query, how to achieve this optimum orientation, so that by optimum orientation I mean time of printing is least surface texture, surface roughness is least, support generation is least. Okay, so what are the possible orientations that I can provide? I can make one like this. All right, then I can have one like this. Another like this. So from ABCD, how do you satisfy all the criteria and why so? A quick question. So public voting, which one do you think is going to give you the, which one of these orientation is the most is optimum? A, B, C, D. Can you
B.
put your vote? D. Yeah, more than you talk, put a vote. Actually, I did not. Continuously, if should be possible if filament is extruded continuously without gaps. Okay. Not quite, Devraj, but we'll come. You'll get the answer anyway. Yeah. So please put down your answers on the chat box. Which orientation is optimum according to you? A lot of vote going to B, 1A, B, B, B. Which printing process? That's a good question. FDM. B. B. Okay. Any particular reason? Why would you think that B has the optimum orientation? Any particular reason to that? One or two answers and then I can go explaining. Support generated is less, all right? Another answer, anybody? One says that the support generated. What about time taken? Will time taken have smoother surface? Okay. Will time taken be same in both the cases? The body will itself, the time taken will not be same. Okay. Which one will be faster to print? Which one of these time will be lesser if supports are not needed? All right. Let's get digging now. Okay. If you are writing now, I will not be able to see, but apologies for the shabby drawing. Okay, say this is the base plate that we are talking about. Okay, nobody said CND, by the way. All right, actually, so yeah, same line. Anybody who would like to change their answer? Right. Okay, that's fine. All right. Say in this case, of course, A is absolutely evident that we will need supports. Okay, I should use different ink. We will need supports throughout the structure. Okay, then definitely by intuition, we can say that A would be the most unlikely orientation that we will carry out. Now, why do you think that this frame will not require support structures? Remember, whenever there is a element of slope, if it exceeds a particular threshold, which in case is roughly towards 35 to 45 degree, if it exceeds that, or if it is within that, then supports will be generated. And further, as you are trying to print these parts, okay, because of friction between the substrate that has just formed and the above, usually tearing of effect takes place. Okay, and as you can see over here, the handle right at the top, sorry, will require further more supports. Let's check out this orientation then. Okay, and this orientation now. Now tell me, which one do you think would be the best orientation? I have drawn the supports. Vote again. Right.
Sir, would the C not require supports in the inside part of the cone?
Yes, that's a good question. C might require support on the inside part. Okay, let's take into account that too. In this case, we would need support the yeah. Okay. Even so, still, which one do you consider would be the best one? D, because you have already given your answers. Okay, so that's the kind of counterintuitive imagination one needs to carry out maybe in some critical looking objects. Now, this was mostly straight lines. One can easily extrapolate how it can be done with other far more complicated structures. So the orientation, as I was talking about in the last class, actually kind of dominates how well the 3D printed part is. Again, a parameter which has little a bit to do with experience. Then again, this artificial intelligence or machine learning algorithms that support this sort of arrangement, okay, where the machine always adjusts for certain orientations that you have done to achieve some output. Of course, the printing time and overall everything will be faster in case of D. Now, you can expect these sort of questions in the NASCOM certification examination, okay, the final one that's going to take place, right? So I believe that was a good exercise for us to cover. I think even in this case, to achieve the top layer, we would need internal support. So this would be the worst, okay, to achieve the top layer. Oh no, top will be vacant, right? Not a problem. Yeah, top will be vacant. So be careful, because when you are considering structures, perhaps here is an outlook that you might consider, that whenever you are thinking about building structures, that is a fundamental part of any civil engineering project, right? So you might want to keep them as and not remove them as such in 3D printing process. So again, the whole concept of structure has a different meaning when you take it to a civil engineering perspective. Again, talking about structures, here we consider the beams, right? Okay, let's take another example. I have to manufacture this plate. Okay. And yeah, within these three orientations, which one do you think will be the most optimum? Again, we draw the line and consider an FDM process. Okay. Yeah. Among A, B, C, which one do you consider will be the most optimum orientation for printing? B. Okay. B. Right. Others? B. All right. So let's quickly draw the support structures. And here it is evident that B is the most fruitful orientation that we would like to. Now, the thing is, let's see how we can optimize support structures by default. Now, what we really want to do with support structure is that we want to have a minimum contact area with the actual body. That is rule 1. Okay. Number 2, the point of designing a support structure is actually based upon the Euler cantilever beam, okay, or Euler support structure. I've critical length. Just let me check it. Yeah, buckling. Okay, so that is one thing that we avoid. So there's a Euler buckling area as well. Plus, we have to make sure that the shearing effect, no shearing effect. Okay, what's shearing effect is, say you have deposited one layer of material which is gradually solidifying, and as you move the extruder from one end to the another and you start depositing, okay, from this particular point, what will happen, this particular shearing effect takes place. Okay, it tries to, have a constant flow over here, and this is something that we would like to avoid. Okay, so then there are so many algorithms recently which are developed for making an optimum support structure. Okay, by the sheer understanding of this case, you will be able to understand how these support structures can be varied. Right? Okay, so as you can see, the variation of support structure and of course the time taken to build this object will strictly, come down if we make an optimum way of generating support structures. So a lot of algorithms are put in place. You can try out and build your own algorithm. That's a very good research in the from the aspect of 3D printing. A very good undergraduate project you can take up or go for an internship to do the same. Okay, so these are the flexibility of how support structures can actually impact the quality output as well as the production time of a 3D printing process. Uh, Pausing here after an hour, I would like to know if you have anything in and out of the topic to ask.
No, sir.
Yeah, I heard somebody, but I could not make out what was the question. Do you have anything to ask?
Sir, here in the second case, the support structure itself needs support.
No, not really. See, like I was talking about, that only after a certain angle of inclination will you need support. So the support is generated such that the optimum angle to the point, to the threshold point where you don't need support will be maintained. Okay, and the reduction of the support structure will be only, the diameter will be only controlled in that way. Okay, let me just give you a quick glimpse. The algorithm will never make a structure that will have a huge degree. Okay, this degree will be controlled to an optimum threshold degree so that the deposition does not need any further support structure. Okay, why? Because you are depositing very little material over here, whereas in consideration to a full-fledged object, you are depositing a lot of material, which creates a good amount of downward weight. In case of support structure, this thickness is considerably reduced, which means that the angle at which you can go on printing without requiring any support is substantially low. Okay, yeah, that's a good question. Anything?
Sir, like what is the optimum infill density, like for printing a solid object?
That depends on two parameters. One, what is the load carrying capacity of your object? Okay, if you want that your object or your part needs to have a very high load carrying capacity or less porosity for that matter, then you will need a very high fill density. But if you want for a prototyping device where you don't care about the strength, it should have the geometric shape as you want it to be, then you can check out the infill density. Maybe tomorrow, what I'll do is I'll show you how my experience from 3D printing evolved with some different objects. Okay, and how the thermal watting. I have some realistic pictures though. I did some experiments at AEC itself. You will see a lot of, problems that occur in these 3D printing processes. Okay, there's only certain amount of height that you can go. Right. Does it answer your question?
Yes, sir.
Okay. Anything? Okay. So I'll stop the screen. I'll switch to a presentation mode. Okay, this will be the next 1 hour of lecture. Yeah, give me a voice cue if you can see the screen.
Yes, sir.
Okay.
Yes, sir.
And now we are looking at an overall picture which you have already perhaps seen, classification of additive manufacturing processes. We have covered almost liquid-based FDM is covered, holographic surface is not covered, layer by layer SGS, I don't think so it is covered, I'm not sure, I did not do it. Okay, solidification of molten material, FDM is done. This is SDM is not covered yet. Okay, so quite a bit of it left. We are going to cover SLS and LOM today. All right. So also DLP, yeah, these and LOM, right? Okay, and DLP. These 4 parameters. I think this is done. This is done. These 4 parameters we'll cover. Right. So I began to introduce how SLS technology is used in diffusing metal into one another. So as you can see in the schematic on the right of the screen, there's a laser, okay, which is shooting a beam to the scanning system. Now, can you recall what the scanning system was? Can you write it on the chat box? Scanning system. What was the scanning system? It is similar to SLA. You can speak up or write it on the chat box. Otherwise, I have to go back, assuming that you did not get it at the first place. Yes? No? All right. Do you remember the galvanometer-based mirrors? Okay, that was nothing but the scanning system. So what we have over here is a mirror. And this mirror is connected to a galvanometer. Now any supply of the current, this mirror will deflect, and thereby it will divert the beam of laser accordingly. Okay, usually this diversion really is not very large, and hence this whole process is now limited to only a certain work volume because of the inherent nature of laser to expand or lose intensity as you deflect it. Okay, that's a diffraction concept that arises. Now, if you remember in SLA, we used laser, which was mostly of ultraviolet light, to uh, start polymerization or rather solidification of polymer resin. Here we are trying to melt metal. And if you consider SLS in particular, it mostly relates to nickel based polymers. Okay, but it is not limited to polymers only. Certain material like glass and ceramic can also be made. The latest that I know of is sand printing. So it's really miraculous to see. Have you seen the video on sand printing and 3D printing? Anyone? Yes, no? Okay, you should definitely see. Look at this idea. In this sand printing system, they are using solar radiation, okay, to just a second, let me, yeah, this is the video. Let me switch the screen. Can you see the video? Give me a voice cue.
Yes, sir.
Okay.
Yes, sir.
So what they are doing is using this reflector panel, okay, not only to get some power into the 3D printing machine, but at the same time, they concentrate the beam to an extent that it produces a high intensity beam of light. Okay, and as you will deflect the scanning system, the mirror system, you can create solid sand 3D printing parts. Very innovative. Again, just there was an insight. For those of you know, you'll be familiar with this microprocessor controller. Okay, there are several switches like I was talking about. I'll paste the link. Yeah, I guess you also can recognize the Z stage of lead screw and the belt connected to a gear and the motor for the X and Y stages, right? Okay, these are the X and Y stages. And that is the Z stage. The lead screw is moving. And it also has a rotary system. That's great. So sand is mostly silica. You melt it up to a certain temperature, it starts printing. I mean, melting the sand, microscopic scale. Now what they're doing is moving the bed, keeping the light source similar. Okay, so this complex structure will be 3D printed. Again, G code and M code, and you pull it off, you get somewhat what you designed. All right, not the best accurate model, I would say, but at least that kind of opens up some interesting domain of 3D printing. Okay, let me share the link to you. Okay, do watch it later. Let's continue with the lecture for now. Okay, So we have this scanning system, and we will shoot laser from place to place. And as you see, there's a roller and a small piston cylinder. I guess you know what's a piston cylinder. Okay, that one you play in Holi. Okay, so you try to displace this so that sufficient amount of material is loaded in this system at the top layer. Okay, just enough. Now the roller will start its motion and it will displace the material into the uh, fabricating piston. Okay, and the moment it does, the fabricating piston will move down. Okay, this displacement will cause one layer after another to be melted, and eventually you'll form the parts. Again, because the solid material is already available in this space, you don't need to create any supports. But then you would need the whole amount of the work volume of the material that you are printing. I was talking about it yesterday. Okay. So similarly, we have a direct metal laser sintering. Okay, it's just that you're straight away putting down metal and using a very high power laser to melt them. What is the next phase of it? How do you ensure that you can generate micrometer or nanometer level of layer? What will be the mechanics? Firstly, it almost translates to powder mechanics or soil mechanics as we study. Okay, uh, understanding exactly how the flow of powder will take place over a media, because here you will get some solid structure. However, over here there are some powders which are again susceptible for compression. Okay, so there is this branch of study where you kind of fine tune these parameters so as to get the most refined layer thickness. Another obvious criteria which arises is the penetration of laser across the layer. As you will realize that this will not be a point in general. Usually the intensity of laser is like a Gaussian plume, okay, that you see in standard deviation plots, okay, where the intensity, the modeling of laser intensity can be carried out by using a Gaussian plume, where the intensity kind of varies in the 3D space. Of course, you can revolve this object and then imagine the 3D space that will be affected by the laser. So the idea is to develop as stringent laser as possible, but then again the cost of optics goes incrementally high with this. And coincidentally, as the intensity varies, the penetration of laser into the material will be same. Okay, that only this amount of material will be under the influence of heat if it is laser. If it is metal, direct metal laser sintering. Okay, this will be under the influence of heat. In case of sand, even this will be under the influence of heat, and hence you cannot assure that you will get a fine concrete element built out of the system. Again, the criteria is that what should be the optimum layer thickness based upon the penetration depth of the layer, isn't it? If you make the layer thickness really small and keep the penetration depth really high, what it is going to go do is also distort the lower layers, okay, which you will end up not getting the part that you wanted with the right amount of surface texture. Okay, right. Then I was talking about certain flexibility that comes along with the laser sintering processes, that you can use 2 or more powders. So these can be evidently divided into further sections where number A will be a single component metal powder. That in this case, both systems are A. Okay, both the powder molecules are A. So as you will provide some heat, the outer molecules of the powder will start to melt because of localized heat, and then eventually fuse into one another, creating the thereby structure. Okay. The next way to do is, if you are using two component of a powder, so in between two A's, I have a B now. Okay. Then the melting point need not be same for both A and B. Okay. So what you can do is, if the melting point of A is very high, say around 4000 degrees Celsius, what you can do is introduce a binder at 1500 degrees Celsius, melt it so that it fuses the two metal together. Okay. Without affecting the structure of A. This is very interesting. All right. The third is, you have the metal powders coated with another material. Okay. So here you have A, where C is a coating that is being offered on the metal powder, and as you melt it, the coating gets melted and fuses the two part of the metal together. Okay. Is this clear till here? I need some feedback. Okay. I don't know if I'm making any understanding any relevant. So is this part clear?
Yes, sir.
Yes, sir.
Right. Thank you. Okay. So these are single and two component powder systems. Can we have more? Yes, of course we can have more. But how would you introduce powders as such? Well, there are different ways. There's something called as, there's something called as CVD. It is called chemical vapor deposition. It's almost like the painting robots in any automobile making industry. So what you have here is that once you get printed, okay, you will introduce certain vapor, okay, of material that will be deposited. All right. So wherever the temperature is high, the subject to addition will be higher in that case. So the third element can be introduced from this section, and you can have three or more, not more, but three different components while making a system. Till now, the research has been done for, quite amount of research has been done for two. As you can see, there's a source which tells you the date as 2003. So that's long back, around 18 years ago. This sort of research has been carried out. Again, what you can do is, just as you see the coating, you can introduce different layers of coating. Okay. And then you can introduce layers of coating sequentially. All right. So this sort of alterations and their study to mechanical strength, then fusibility can be addressed, and then new structures can be brought with better properties. So as you can see here on picture on your left is raw nickel alloy copper powder mixture. Okay, this is raw, and then raw copper coated nickel alloy powder. Can you see the structural difference here? There is an outer structure, okay, of powder molecules, whereas here it is there. All right. So nickel, copper are separated. Here, one is coated. So evidently, there is a great amount of difference in structure as we proceed with powder-based coatings and just physical addition of powder. Okay, there's a good amount of difference. And post-sintering, what's the condition? This is, as you can see, once the metal has melted or sintered as we speak, it has fused. Not all the metal has melted, like in a casting process, where all the material is liquid and then you make it flow into a mold. We'll avoid that. So here, the inner composition remains homogeneous, and then you get a good binded object suitable to use as a product. Okay, so in the figure, as you can see, that there's a canal over here. All right, and these two land parts are to be connected with this bridge. Can you see the bridge now? Okay, and what you see here is that two robots are actually welding the bridge, or rather making up the bridge, as they are sitting on top of it. Now this is really interesting, and this is done by a civil engineering company who's using robots that can weld, and the concept of welding into structures. Okay, so what do we need? We need a robot that can weld. As you can see, it has been welding, and as you know, you must have gone through first year workshop. So what is welding? You get an electrode where you have a metal with flux embedded on the periphery. You take it to a temperature which is higher, you melt it and put it on a substrate, right? So instead of a substrate, you deposit the weld elements sequentially, okay? And then what you end up is metal welded together to form a solid structure, okay? As you can see, this robot is doing the same. So 1 plus 2 gives you this, a solid cast iron bridge entirely made by 3D printing process. Now, what's the benefit? I mean, will it be cheaper? Will it have better rigidity? Please take a look on the structures which are present below. This is the most important part where conventional manufacturing will fail. Why? Because the topology optimized structures as such will be the best component for any load bearing condition. Okay, why? Because you would know that in place of this, if I would have put a solid metal bridge, the weight of the metal bridge itself would have been sufficient enough to collapse, isn't it? I hope you agree with that. The weight of the metal bridge would have been sufficient enough to collapse the bridge. Now, because I have printed the parts in such a way that these only form an interconnected web of structures, the weight associated with it is considerably high. Also, it will not lose any strength due to this particular construction. Okay. The third thing is that this process is not creating any aberration to the external environment. All right. We are not generating any support structures throughout this bridge building process. And we are relying on the fact that as the part is being made or being welded, the utilization of the bridge will obviously be carried out, which means it is already being used. Okay, so this is a remarkable development in 3D printing, considering large-scale constructions. So another example I would like to point out, yeah, this is the welding, okay, and this is the topology optimization. As you can see, from a solid bridge, you run an algorithm where it cuts down the material. Okay, if you ask any expert who has been involved in manufacturing such parts, will straight away reject this part because it cannot be manufactured with conventional objects. But with 3D printing, this is possible. We have seen that. Go to any shape, and with this topology optimized structure, you get the complete bridge. I'm not sure which place was it. I believe it was Netherlands. But you can. This video is available. 3D printed metal bridge. You can have a look at it. So the second iteration of this particular process, I have just moved from SLS, just to give you a cue why we are talking about this. I have moved from SLS, understanding that metal can be printed, to how large scale printing can be done, because SLS had a limitation, okay, of only working with small volumes. Here the concept of welding is introduced to print metals. Now it uses what? Robots. It uses topology optimization, mechanical welding, and the concepts of civil engineering to make a bridge. Now this example over here is somewhat different. The material that is being used is nothing but concrete. And instead of a robot, we are using something called as a gantry. Okay, this is the simplest form of XYZ stage. I would not call it a robot, but of course, XYZ stage robot that was available right from the beginning. If you have visited any railway industry or a large heavy industry, you would always see a gantry on the top roof rail, which is used to carry different heavy equipment from one place of the factory or the shop floor to another. Now, the same technology is being used to move this concrete extruder that is being fed to build this house in an automated fashion. As you can see, the completed houses are over here. And what you see here is the layout of the other houses that are to be completed. Now, this is an entirely different process. Instead of a robotic arm, which is a little expensive, you can straight away go with a gantry. How will it operate? If you remember the motor belt system, the same concept can be applied over here. So basically, this is nothing but an FDM 3D printer, but it uses concrete. Okay. A little pause. Any questions related to this?
So these buildings will require manual labor to put up structure supports, right?
Sorry, manual labor to put out support structures where?
We cannot put cement over wet cement. It will not solidify as quickly.
Exactly.
So we will need supports beforehand.
Right. That is an excellent question. Yeah.
Yes. Will you answer?
No, sure. Please go ahead. I have no background in civil engineering.
Yes, actually. Yeah. This 3D printing technology in concrete, when they are used for concrete, actually some additives are used. They are not like day-to-day concrete that are used for normal construction. You must be aware of there are different kinds of cements as well, like rapid setting cement, which are used for underwater structures, where the concrete has to be strengthened, at a very rapid way. One layer gets late, and the arm comes, and it will take time to come back to the same position once again. So by that time the layer will get solidified. Okay, so some time gap has to be there, like it has to get solidified, like when the arm comes back to the same position. And again, it should not be that rapid in getting solidified, that just after coming it doesn't get its shape. Are you getting my point? It should be like in a state which will be in between getting solidified when the arm comes back, and also to not that much solid in state that when it comes out of the nozzle, it gets solid. It doesn't get proper time to take its actual shape. So some kind of time duration is fixed. That I don't know. I am also not that not from that particular area, but yes, some kind of additives are used to play with the setting of the cement. So the how to play with the setting of the cement, that is under, now nowadays they are being studied in most of the IITs. This 3D printing concrete. All right, Juan, you would like to add
Yeah,
something?
great. Thank you for helping me out. That was a great answer. Actually, I learned a lot about it. Yes. From the information that I have is the latest trend in 3D printing is in relation to civil engineering, as because the scalability is pretty high. Uh, we are not talking about only structures which can be made at that point. We are talking about maybe some bricks that can be rapidly made and then distributed across. Okay, the manpower related to shifting of things will not be necessary. uh, Again, this sort of technologies, as I was talking in my last class, are used in underground, underwater storage facilities. All right, and they send these 3D printers of gantry system, and then they start building, either use their own concrete, or they can use the sand that is available right away on the ocean floor. So this is perhaps one of the takeaways for people who are associated with civil engineering to direct themselves into 3D printing, because this has been a primarily mechanically dominated discipline. However, now because of applicability, it can just take any form and shape. So I believe what you have learned across the process will be relevant in a couple of years, even in civil engineering processes. All right. Yeah. Moving back to the presentation. So the benefit of having this gantry system is that, of course, it has the same benefit as a robotic arm, that not only you can start depositing the concrete layer by layer, you can also use some auxiliary systems like placing bricks and placing thin, roof sheets, okay, and windows along with the gantry system as an attachment, and then carry out the process. One backdrop is that you need a really flat rail for this gantry system to move about. Okay, any undulation in the system leads to uneven structure, which again promise is leading to a promising field where how do you make this structure actively leveled, which means that by using some spring mass damper system, you are going to actively stabilize the system, and it does not matter if you are in an uneven ground, it will stay level, and the 3D printing process will carry out. Okay, so if you someday come up with a company which can do that, amazing, you'll be a millionaire in no time. All right, so that was about concrete based 3D printing processes. We will move to DLP 3D printing features. So DLP, digital light processing. By far, I believe this is the most advanced and promising form of 3D printing structure. Just look at the image of this DLP structure and look at the range, 500 micrometers. Okay, that's really small. All right, I mean, couple of hair, human hair, and you can build a complex structure with that amount of surface roughness. All right, so what is the fundamental concept? We are replacing the laser and mirror with a projector now. So as you would imagine, what is a projector? It beams images, okay, light of images onto a screen. So here, instead of a screen, what we are doing is beaming images on a layer of substrate, okay, or a resin, whatever you would like to call, which implies that this particular layer in the structure will be made at one go. All right, this will be fabricated at one go because we are not making a laser move from point to point over here. What we are doing is exposing the surface of resin to a single beam of light. All right, that is the advantage. And the applicability is that the same resin or polymer can be used to carry out this process. So perhaps we were limiting ourselves that the resin is not fluidic enough or the laser cannot penetrate further, but this changes everything. With the same resin, you can use the DLP process. I'll come to the structure of it, then perhaps you will realize how this machine works. Okay, even though it is generating layer by layer, not like scanning way, but single layer deposition, you will quickly realize there are no support structures even for steep angles as such. Okay, the support structures are not available. Why is that so? Okay, we'll look at it in the next slide. Right, so this is something called as a DMD chip. Okay, so as you can see, it is nothing but a mirror. All right, and this is a chip which consists of mirrors, small mirrors, which are assembled. This mirror itself are of 1 micron of width. Okay, so every square inch you will get at least 1 million of these chips. Again, each mirror is controlled similar to a galvanometer, which means that beneath each mirror we have a galvanometric arrangement with coils, okay, which will deflect a needle on top of which the mirror is placed. Okay, so actually this concept is already established and projectors use them. Okay, so how do a projector work? A projector actually beams different color lights on this DMD chip, and based upon the deflection, if it is 100% deflected, it will usually generate a black spot. If it is 100% in alignment, it will create a light spot. So whatever comes in between will be treated as the difference in contrast. Okay, so if you project different color lights, so you have 3-4 bulbs and you project different color lights, so the very motion of these DMD chip will now make movements. Okay, this motion of this chip will make the image move, and if you project that image, say the image is in ultraviolet range, what you will realize is that this ultraviolet range projected onto a resin will solidify the material. Okay, and that is how a DMD system works. Again, say I have a cone. Okay, I will make slices of this cone, which will only turn out to be circles, isn't it? So here what I'll do is I'll program the chip in such a way that it will deflect those mirrors which are bounded by the locus of the circle. Okay, only this will get deflected. All right, and if you want, if this will be possible if it is a hollow, what you call cone. If it is a solid cone, all this mirror will be deflected. So that's a digital information that I need to send to this DMD chip. So what you understand is that the fabrication is not only fast, but it is extremely digitized. Okay, so digital DLP, digital light processing, and by the sheer action of one single burst of radiation, the whole surface will be formed in one go, and that will give you 100% density. So does this answer the question that how are you going to achieve 100% density? Did you get it? How this links to our question, 100% density?
Yes.
Yeah,
sir.
anyone? Yes, sir. Right. Okay, so one drawback leading to another information. Okay, so I believe if I start DLP now, if I finish up with DLP, there'll be laminated object manufacturing left. Okay, yeah, let's see this example. this is from SLA, okay, and this is from DLP. All right. So almost similar level of refinement, and the rate of production is extremely fast, and you will not see any staircase effect, any scanning problem over here. 100% solid material formed out of a DLP system. Again, because of the control parameters, and you don't need much of stages over here, you need a very active scanning system. You will incur a lot of costs. So DLP printers as such now are although available, but they are very costly. Okay, so here just let's go through the schematic. So what we have is a mercury lamp, okay, going through a 365 nanometer filter. Right, I actually forgot what's the wavelength. I'll show it in the next class. What's the wavelength at which photo curing takes place? Okay, then we have this electrical shutter. If you would recall how we switch on and switch off lights. Okay, collimating lenses so as to focus the beam, avoid diffraction. Okay, and then reflecting mirror going into this DMD chip. Reflecting mirror going into this DMD chip. And this DMD chip will be controlled by what? By the controller of the computer. And all you need to do is just have a Z stage, okay, to change the depth of the system. All right. Then you have something called as tube lens and objective lens to scale the image, because the DMD chip will not be more than 1 centimeter by 2 centimeters of size. Now, of course, this should limit your volume. So what we can do is scale the system by using different objective lenses, which will eventually create a larger work volume for the printer. And there you go. This is a DLP printer. Okay. Right. So before going into laminated object manufacturing, let's talk about some subtractive manufacturing, which looks like additive manufacturing. So here, as you see, is a piece of foam that is being cut out layer by layer, and only to form, this object, which otherwise would have been 3D printed. Okay. Now this same concept is being applied with LOM. All right. So LOM being the last of the processes that we will discuss today, laminated object manufacturing. Okay. So let me switch back to the drawing board, and I'll just show you what schematically how LOM is available. Okay. Let's see. Right. Okay. Please give me a voice cue if you can see the OneNote background. You have only 15 minutes. Can you see the background? I mean the screen. OneNote.
Yes, it's visible.
Oh, great. Right. So what is laminated object manufacturing? Again, 100% density, remember. So what we are trying to do is we have a sheet of any material, and say we have a pyramid, a solid pyramid to make square pyramid. So what it will do is it will first lay out all the sliced parts, okay, sequentially. All right, and so on. Okay, and instead of a one single sheet, it will be laid over a continuous roll of sheet that is available. Okay, so here a continuous roll of paper or whatever you require, polymer sheet. So you will place, and there's a small laser with a scanning system which will cut out these parts, all the edges of it. Okay, and beneath this will be a tray on which each layer will be deposited by some rollers which are fed with adhesives. So what happens is, once this part is cut out, it will be placed on the plate and the Z stage plate will move down. Okay, it will come down, the Z stage. Once it has moved down, this roller will pass and stick some glue on top of the surface. Okay, then this part will be cut out and this roller will be displaced counterclockwise, which means it will move in the negative X direction. Okay, so we will be aligning these two parts, and again it will be moved up, it will fix it, and then it will move down. Okay, so as you repetitively do this process, you will stack laminas one after the another, and eventually leading into the prism structure that you were originally willing to make. Okay, the downside of it is that instead of this process, instead of doing it sequentially layer wise, what it does is that it entirely fixes the whole sheet of the work volume along with the object, which means that you will only be able to see the tip and you will find a whole bunch of paper layers. Okay, instead of adding glue into only one piece, this will add glue the whole paper and it will repetitively snap the paper for the working volume and go on pasting. So you have the prism eventually, but what you have to do is cut out the parts out of all the material only to find the prism. Okay, the Z stage that I was talking about, which eliminates this process and saves a lot of material, is the latest technology that is available. Okay, initially it was very rudimentary and the whole set of paper was destroyed. But the best part of it is that instead of using very high quality material just to make a prototype, you can use paper which is already available. Only thing that you have to do is just cut it with laser, which is even more convenient because these laser systems will be only of 2 watt strength. Okay, so that's a low power, quick, rapid prototyping system. But with the oncoming Z stage, this whole process of depositing the whole layer of paper gets eliminated. Another advanced feature which is available in layer object manufacturing is that now composites are being used. Because you can use different sheets of different materials, it is not mandatory that you use the same sheet material over and over again. You can use different staggered layers. Now this increases the flexibility of building composites immensely, because with laser, not only you can cut the sheet, you can also melt some adhesives with certain amount of heat which are embedded in a sheet. Consider this as one single sheet. That's material number 1. That's material number 2. And we have adhesives over here. Okay, so with sufficient amount of laser power, it will cut through the object, the slice, but with just a little less power, it will melt the adhesives, and this system will get stuck one after the another. Okay, this is how composite material fabrication can be done through this LOM process. Well, that's a quick overview. I'll give you some photos later tomorrow. I believe we are running short of time. Yes, final 10 minutes just to entertain certain doubts if you have. Okay, that was all for today. Maybe I should not extend it 2 hours. It's too much information, I believe. Yeah, so any information or feedback that you would like to give, or anything about 3D printing that you would like to know, because I believe tomorrow would be the last time I'll be taking a class. So we'll cover some attributes of 3D printing, like in general, not relating to any process. So any feedback or any topic that you would want me to cover, or any doubt that you have for now?
Juan, are you familiar with reverse engineering technique?
Yes, actually, a very interesting fact though, we have a 3D scanner at AEC.
Really?
Yeah, we have a 3D scanner at AEC. I was using it for a while, but it needs a little experience. So right with the FDM 3D printer in the sustainability lab, we have a 3D scanner where you can take any object, scan, make a 3D STL file, and then give it to print.
Okay, so there is some kind of it is some kind of box, I think, where the instrument is, the object has to be placed and it will scan. Or
actually, no, it's just a light source. That's all.
Okay, so
it's just a light source with a detector. Yes.
In one of the videos, we saw that when the object is scanned with a camera, the noises, they call it noises, like the image of the background and all those things. Correct. They disturb. So it has to be removed again in a software. So directly the STL file can be exported, or some kind of modifications.
Actually, this image stabilization techniques are already incorporated in the software. We can adjust the levels to what refinement do we need. And there is a feature in what I was working on. I believe it was called AdWorks. That company which has installed the 3D scanner actually makes 3D models of cars. You consider any car, Nissan or Hyundai. They get the car, they make a full 3D model, and they make animations out of it for stunt and everything. So that's the company's prime target. Otherwise, they are into education and stuff. So what they use is they use this scanner. After which the scanning, what they do is they override with some flat surfaces, just like we do 3D modeling. They connect some dots, and between the dots there will be a flat surface. So that kind of assures that you will have a straight object, and this surface noises disappear. One more thing is that these scanning systems are incapable of actually penetrating through the object. So if you have if you have a bearing housing where there's a hole in between the object, it will not be able to detect it. So that's one downside. So there are other features like tomography, CT scan methods, where the whole objects can be made. I can cover a session if you want me to give a half an hour how this image processing actually takes place.
Okay, so like theoretically, at least if you can, show the process system, how it is done step by step, then it will be beneficial for them.
Okay, I'll make a section tomorrow for this image processing in 3D printing.
Right. Okay, that would be good.
Okay.
Yeah. Participants?
So if you do not have any question, we can close for today.
Questions they will not have, but is there any demand?
Yeah.
Because Juan is the right person to ask. He has been working in 3D printing for several years, and if not tomorrow, then never. So if you want to know something, please tell, and maybe later in the group. But yes, by today only, because he also needs to prepare the contents. So I think there is no demand. That is, I don't know, good news or bad news. Curiosity level.
Yeah, you can ask me later, no problem. I'm always available. My mail ID is available. My phone number is available. Any queries, I'll handle. No problem. If you have something for tomorrow, do let me know. I'll give some presentation regarding it. So perhaps we can close now.
Thank you.
Okay, thank you so much.